Okay. Hi, everybody. I'm Samaya Madhavan, and I'm a software engineer with IBM. I'm also a developer advocate, where my day job involves developing and publishing content around, machine learning and deep learning. And I am here today to be presenting about the fundamentals of deep learning and how artificial neural networks actually links with deep learning, and and also the talk is going to be around how artificial neural network is inspired by the human brain. So do have a few disclaimers. In this talk, I'm only going to give you a very high level understanding of what deep learning is and artificial neural network is. So at the end of the talk, you'll be getting an end-to-end understanding of how an ANN is or an artificial neural network is developed. And also the key terminologies behind it. I will walk you also through a Python code on how the code is being developed. And hopefully just spark some interest in you all, so you can go in and learn much deeper about it. And also I'm not going to be talking too much of math in this session, because one thing I've learned is when I start talking too much of math, people just start getting distracted and lose interest. But at the same time, I'll be talking a little bit of the formulas that come into play, but also at the same time I'll abstract the formulas. That way, you don't have to entirely understand the formula, even if you don't. Um, Okay, so hopefully you guys have my screen again. So the thing that I do want to say is that I do not have a background on neurology. So everything that I'm going to be talking in this session is going to be very high level understanding of what a human brain works. And that's the extent of what you need to know to understand the session. So with that said, let me walk you guys through the agenda. I'll begin by introducing about deep learning and where this space fits within the realm of AI and data science and everything. And then I'll move on to discuss about why deep learning is popular today, more than before. And after we discuss about those points, I'll show an example. I'll show you the correlation between a neural network and the human brain. And as an example, I'll show you an example how a child learns its fundamentals, and relate that to how a neural network can be trained. So I like to get the fundamentals out. So I do get a lot of questions around, if deep learning is a competitive technology to machine learning, if, deep learning has come into place to replace, machine learning, which is not true. Deep learning is a subset of machine learning, and I'll be discussing about why deep learning is been gaining immense popularity in the slide to come. But also there are use cases where you can still practice machine learning, and your model efficiencies are even defeating the metrics that a deep learning model can perform. So it's still deep learning is an additional option to the other algorithms that machine learning has to offer for us today. Um, so we'll move on to discuss about why deep learning is popular today. Just give me 1 second. Yeah, we'll discuss about why deep learning is popular today. So the first reason being, there is enormous of data today, more than before. So just when you wake up from your bed and you scroll your phone and you click on Amazon, and then you click on what products you like, you check WhatsApp, or every day-to-day activity of ours is producing more data that some an organization can learn information from you. So and deep learning algorithms are data thirsty, so they need humongous data to unveil hidden patterns which was previously not available. The second reason why deep learning is popular today is the availability of the compute capabilities. So a typical deep learning model, if it were trained on just a CPU, would take days or weeks, versus today we have GPUs available to us so very easily, and with a GPU you can just train these models within minutes. So that's the range of enhancement that you get with like using a GPU over a CPU, and these are very prevalent these days. But also, most importantly, there's a lot of algorithms that are within the realm of deep learning that are being built today. So that actually helps us, gives us a lot of option, and model performances defeat each other with the advent of each of these algorithms. So with that, I want to introduce to you the most fundamental architecture of deep learning, which is artificial neural network. And you'll see how in this picture over here, I just wanted to like compare and correlate how in the bottom we have an artificial neural network, and in the top we have a snippet of our brain cell, which is a neuron. So to highlight some of the correlation is neurons are highly connected, and so are our neurons in our neural network. And then just like how our brains communicate these like chemical signals through like synapses, uh, the neurons within a neural network also communicate with like data, right? So these are some of the observations. Just wanted to like throw a first look of what an artificial neural network looks like. So I don't intend for you guys to like grasp a lot from this image, but we will be digging deeper into the functionality of an ANN in our future slides. So on to our next part. So right now I want to talk about, think about how a child learns. So let's assume this is a child, and the child is learning some of, the objects that it's presented to it. So for example, it learns about an apple. So it, in the past, it's probably held an apple, or it's seen images of apples in a chart, or on the TV. And then it probably took a bite of an apple to know, what the texture looks like, or like, what it tastes like or smells like. So it's got, various features through which it can understand what an apple looks like. And so suddenly one day we come and we present an apple to this child and like ask him, or her, like, do you recognize what this object is? So maybe it does some thinking, and then it probably says, I think it's a tomato. So what happens is it sees the apple, it does some processing in its mind, and then it makes a guess and it says, I think it's a tomato. So this person or the caretaker that asks this question comes back with a feedback. It does some, she or he does some error analysis, and comes with the feedback and says, I probably understand why you thought it's a tomato. Maybe because it's red, and maybe because it's round. And good job that you think they're similar, but you're not quite there. So they calculate the error and they give them the feedback. So this child now takes this feedback, and then goes back and thinks about it, and everything happens within the brain. And then goes back and takes a look at this apple probably and thinks, okay, so this is probably the difference. So it processes all that in its brain. And then again, it comes back and thinks about it, and then it probably guesses it right. So it comes back and says it's an apple, right? And this time, the person that asked this question comes and gives the child good feedback. You probably clap your hand and say, "Great job." So now this again is like taken back into the brain, and the child now processes it, and it reinforces its thought. So do want you guys to observe that there was something first in the forward direction that went in wrong, and then took the feedback, came back, fixed it, and then took another pass and made the right guess, right? And in the next slide, I'm going to present to you a first look of how the neural network actually processes data. And I understand that this looks very overwhelming at this point, and really the only takeaway that you should be taking is that there is a forward pass, data is being processed, and there's like input over here, and there's like that it's trying to make predictions of what the output should look like, and then it's processed that output, and then it now sends some feedback, and then that's being fixed, right? So let's dig deeper into what happens within this neural network. So two steps, as we saw, is the forward pass and the backward pass. But before I get to that, let me explain to you what a shallow neural network is. So a neural network, like we saw, consists of three layers, which is the input layer, which is where your inputs are passed into the artificial neural network, and then the output layer, and in between is what you have, a hidden layer. If you just have one hidden layer, it's called a shallow neural network, and if you have multiple hidden layers, it's called a deep neural network. Um, so that's for the basics of how you define a neural network. And in this forward pass, let's see how what happens within, to begin with. I just put this image back as a reference. So I'm going to tell you what happens within each of these individual neurons over here. Uh, so within every neuron, two things happen. First is how you calculate the weighted sum. So let's assume, if you want to go back to your predicting if it's an apple or a tomato, situation. Let's assume we have three columns, right? And then we have the output column, which would predict if it's a tomato or an apple. And then the three columns, we can call it like color and the shape and then the texture, right? So we take one row at a time, and then the first row is now being passed in as input, which is x1, x2, and x3. So that's being sent over here, and you assign to these, inputs what's called weights. So let's assume that this particular neuron is thinking that I think the feature for color should carry more weight in me trying to predict if it's an apple or a tomato. So let's say it gives zero point 0.8 as the weight, and then the other two is given like zero point 0.1 as the weight. So in this example, this particular neuron considers that zero point 0.8 has more, I'm sorry, color has more importance than the shape or the texture in trying to predict the fruit. So we calculate the weighted sum, which is the summation of the weights and the inputs multiplied, and then we add a term that's called the bias, right? Um, and to this output, we apply what's called an activation function. So remember how I said these steps happen within each of these neurons? Let's assume that this particular activation function comes with outputs which are like, of the values 10,000 something, right? And then the next neuron comes with with a value that's like zero point 0.5. And for the next layer to, make sense of what comes out of this activation function, you see that these scales are very vastly different, which is why you apply an activation function which would bring the outputs of the previous layer into the same scale. So for example, the sigmoid function converts any value that you pass into it within a range of 0 and 1. So that's what you potentially do over here. So this calculation, this computation happens for all neurons in the neural network, including the output layer. So eventually it's going to come up and guess and say, I think it's 0.1% probability that this is a tomato, and it's a 0.9% probability that it's an apple, right? For example. Um, and also, what happened, like, for the sake of understanding, I'm telling you guys, how these neurons actually function, but really the insides of the values inside each of these neurons are not perceivable. So, so the next step is the backward propagation, similar to how we saw that the child predicted a value that was wrong, and an error was analyzed, and then the feedback was sent back, and another set of processing happens in the brain, right? So let's assume that the inputs were processed, and then it came back and it said it's 0.9% a tomato. So the output of this one would be a tomato, but while in fact the input was probably a pineapple, right? So in this case, the actual value is a pineapple, but the prediction was a tomato is too far away. It's not very relevant. So what's going to happen is we're going to come with identify the loss And we're going to say the loss value is, too high between, like, the actual and the real value. So something needs to be fixed. And what will be fixed over here are the weights. So it's going to, like, at each level, it's going to change the weights back. And to calculate these weights is what we use, a gradient descent. So think of gradient descent as a marble that's like put inside a funnel, and then you want to swirl it, and you want to, and that there are like several lower points. So you want this marble to get to the lowest point, which is the point of least loss, right? So at that point, your value is very close to the expected value. So you go back to the weights. So remember how, the initial neuron, assumed that the color was the most important, aspect. So maybe it's going to go and fix that and say, I don't think the weights for the color should matter a lot in me trying to predict uh, um, what type of fruit it is. So it's going to come back and adjust the weight and for this and say, I'm just going to give it like zero point 0.3 instead of zero point 0.8 that I did previously. Um, and this is going to happen in a cycle, right? So there's going to be a forward propagation where each of the neurons are going to try and predict the final output. And at the output cell, there's a loss, which is being calculated. And the feedback is sent, and it's sent back, and we apply gradient descent, and which is where, a lot of these calculus related mathematics come into place, where you calculate the derivative, and then you find out how much my weight needs to be adjusted to make the loss eventually smaller. So it happens in a cycle. So the backward propagation happens, and then you again, the neural network again starts guessing the output. So it's a repetitive process. So uh, there are, like, more concepts and more, like I said in the beginning, this is just a high level end-to-end understanding. There's something called, learning rate, which you which will determine how much of the weight you want to change, based on, when you've gotten the derivative of the weights, right? So there are a lot of, like, pros and cons in using each of these values, and challenges. And This session was intended to be covering the basics of it. So I'm going to walk you guys through, and that will actually give us an example of the neural network from start to end. Let me share my screen over here. In here, I'm using IBM's cloud environment. It's called Cloud Pack for Data, wherein I've imported a notebook that'll show you an example of how a neural network can be built from start to end. So there are several frameworks that help you in building a deep learning model. TensorFlow, which is right now integrated with Keras, is one of the popular framework that's out there. It's also in Python, and there's also PyTorch, which is super famous. But for this code walkthrough for us, I decided we'll do the NumPy way, because what happens with these famous libraries is a lot of these internals are abstracted, and so this whole process of understanding is masked for us, and the entire it's just going to be one line of code to implement what's in there. But I'd really, for like beginners, encourage you all to just go to the basics and, like, learn from there. So in here, let me start with saying that X is an input array that's going to be used for training per se. So we have like 4 entries with 3 features each. And then Y is the output array, which is the actual value. And these are 2 helper functions. The sigmoid function, like I told you, helps you mask the outcomes of each neurons to between a value of 0 and 1. And the sigmoid derivative will be used in the backward pass to calculate how much these weights needs to be adjusted. That said, this is a definition of a neural network. We begin by initializing, so this is assuming that we have 2 layers. So we have weights 1 and weights 2. The input, which is X, and Y is the output. And the output over here is the output that the neural network is going to predict. right? So y is the actual output and output is the predicted output. Um, so the shapes and sizes of these are initialized. So we begin by initializing it to a random number. If you remember how I said I'm going to initialize the first weight to zero point 0.8, so you could initialize it to a number of your choice, or you could randomize it, or you could set it to all zeros. But you'll see that if you actually chart out these weights, the model is learning and adjusting these weights to make the model perform well. So the first step is the feed forward, wherein the dot product, which is the weighted sum, and then you apply the sigmoid, which is the activation function. You do that for the first layer, and then you instead of the input, you pass the output of the first layer for the second layer, and then that's your feed forward, and then your feedback or back propagation. This formula is over here is a little involved. So it's basically expanding on the formula that I showed you guys on the presentation. So it uses this sigmoid derivative helper function that I showed you, and then you adjust the weights. And training is nothing but doing this, in a loop. So you first take the feedback, sorry, you just feed forward, you make the output, which is the predicted value, and then you apply back propagation to it. And then here's where the action happens. You just initialize this neural network, and then you do it like about 1,000 to 1,500 times to see if your error values, you want the error to be like close to zero. Zero value of error means that your model is predicting values the right way. But there are also, like, if your model has an error of zero, this potentially a chance of overfitting. So there's like logistics like those involved. So in here, so every 100th iteration, you're going to print out what the value, what the input value is, what the actual output is, and what the predicted output is with the loss. And then we kick the training, which is going to happen for 1,500 times. So I'm going to let this run and show you guys what it looks like. So the first iteration, the actual output is, for this input, the output is 0, 1, 1, 0. But the predicted output is all a little over 6, which doesn't make a lot of sense, but the loss value is also relatively higher. And then if you keep, analyzing each of these iteration, you'll see that the loss value is reducing and the values are getting closer to the actual output. And so each of these runs will keep working towards attaining the global minimum, which is a terminology involved in calculating your back propagation. So at the end of 1,500 runs, you'll see that the final values are very close to the actual input. So in here it gets to 0, close to 1, close to 1, close to 0, and your loss is also at its lowest point. So that was everything I had in terms of my slides and my walkthrough. Yeah, so hopefully you guys enjoyed this. Please do give me feedback, and I'm open to taking questions.
Thank you